Right, so now we're looking at the second set of for electrodynamics of notes. Well, second part of it, and what we're going to do is we're going to do the motor, and then we're going to look at the calculations. So, the electric motor is the opposite to a generator in that the electric motor uses an electric current, doesn't create one. So the current in a coil is placed in a magnetic field. So now we have a current, okay, and so it's the opposite. We'll go through it. Current in a coil that's placed in a magnetic field. This will rotate. This is known as the motor effect. The force experienced is the greatest when the conductor is placed at right angles to the magnetic field. In other words, when it's flat, and the force experienced is zero when the conductor is placed parallel to the magnetic field when it's vertical. We're going to use the right hand again. This time though, once again, your fingers go towards your south pole. That's never going to change. But your thumb now must point in the direction of the current, and your palm points in the direction that the coil or the wire is going to move in because of the magnetic field. Okay, so there's an interaction between the magnetic field created by the current in the coil and the magnetic field itself from the magnet that we have it in. Okay, and as a result, the coil will turn, and this is the motor effect. So this is quite important. Now, the reason why I like the right-hand rule for both of these is because your palm is always your unknown. In a generator, your thumb points towards the force, and your palm shows you the current, which is what we want to know. So the direction of the current. In a motor, your current is shown by your thumb, and the unknown is the force, which is your palm. Okay, so a simple DC motor means that you have a coil of wire, okay, which now you have a source, a power source, okay, and it's a DC motor, so we have a commutator. The power source creates a current inside my coil. That current then forces the coil to move. The coil of wire placed inside, we have a commutator. Okay, please, it's very important. Then we have our carbon brushes with the commutator, which then connected to the external circuit. And the point of the commutator is that it ensures the current is reversed in the coil as it goes along, which is very important, because if that didn't happen, the coil wouldn't rotate. Okay, it would actually get stuck, which is what we want. So now, at this juncture, please, there is another video in your teams called How a DC Motor Works. Please go and watch it. It really does give you a very nice explanation of how a DC motor works and how it rotates and what happens with the magnetic fields. Okay, and it's animated, so it makes it a lot easier to understand. What affects the power of an electric motor? Well, increasing the strength of the magnetic field. Please. Okay, the point here is that, please, you can't say a bigger magnet. This is about using a stronger magnet. Okay, increasing the current in the coil. So in other words, make the current stronger by either making it a bigger power source or by using a coil with a smaller resistor. Increasing the number of windings, so putting more coil, putting more wire inside the magnetic field, or wrapping the coil around an iron core. An iron core makes it a stronger electromagnet. Okay, very, very, very important. Okay, so when we look at alternating current, which is what an alternating current generator creates for us, first we've got to talk about why do we use alternating current. Well, the advantages of it is that we can step it up and down. So we can actually change the value of the AC current, which is really important for us when we transmit it. AC voltages can be stepped up at Eskom, then transmitted over our power lines at very, very high voltages and very, very small currents. And the whole point of that is to minimize power loss due to heating. The smaller the current that it gets transmitted at, the smaller the amount of current we get. It's easier and cheaper to convert AC to DC than to convert DC to AC. And AC motors have a better power output. So they're more efficient for us, which is what we want. Okay, so the waveform which you've seen before, okay, is very simple. So electrical generators at power plants produce an alternating current that's then transported to our homes along the national power grid. The AC voltage is continually changing from 0 to a maximum, which is called Vmax, very logical that, through a 0 back to a negative maximum. The fact that it's positive and negative really is irrelevant because that's just a direction thing. For South Africa, that repeats every 0.02 seconds. So we create electricity at a frequency of 50 hertz that you do need to know. When we look at it, our electricity supply goes through to a maximum of plus 311, all right, volts, and to a maximum of minus 311. Now, if you think about any appliances you may have bought, if you look at it, it says to you that the voltage rating is 220 or 240 volts. Now here I've got 314, but that's okay because the voltage they're referring to is that value over there, which is the VRMS value. This is an average value, and this is the value that's actually important to us. We'll talk about it in a second. Okay. And it's a better value for us. We can't use the maximums. Plus, if you look at it, the maximums are there less often than the averages, and it's an average that's been worked out using trigonometry. You don't need to know how to do that. Luckily, they were just going to give you the equation, which is even better. Also, if we look at a current, though, current goes through the same thing. But if you look at this current, there's no values on this graph because the current you'll experience in your home depends on the appliances you've plugged in. So current is very dependent on the amount of resistance that it is getting. So we can't put a value on that. But once again, positive maximum, negative maximum, and then we get an RMS value. So that RMS value is the average that we would use. Okay, it's very, very important. We're going to talk about that value in a second. When we get to power, though, average power is more useful for us than maximum because it's at the maximum for such a short period of time. But because power is voltage times current, okay, you never get a negative power. You can't, because when current is positive, voltage is positive. When current is negative, voltage is negative. So either way, you're multiplying two positive values together or you're multiplying two negative values together, they'll give you a positive answer. So that means the graph for power looks slightly different in that it never goes through a negative. This is the 0.04 that we had just now. This is the 0.02 in terms of time. Okay? So the point here is that power gets to a maximum and we get a bottom. Now here, this average literally is the top plus the bottom divided by 2. Top, bottom, divided by 2. All right, we can't do that. If we go back to this graph here, we can't take the average as being maximum plus minimum divided by 2 because we'd get 0. So it doesn't help us. Okay, so let's talk about the root mean square. The root mean square is defined as of an AC is the DC potential or current which dissipates the same amount of energy. In other words, if I tell you that I have a VRMS of 12 volts, it means that I can replace whatever is needing that 12 volt RMS value. I can take a battery, a normal DC battery that has a potential of 12 volts and replace it with it. And I'll get the same effect. Okay, so VRMS of 12 volts means it's 12 volts DC, direct current. How do we work out the RMS? Well, we take the maximum value divided by square root 2, root mean square. That's where it comes from. IRMS will be the maximum current divided by square root 2. You will be given these values. So average power, now here, and also with this one, These subscripts are non-negotiable. You have to. I'm hoping you're getting this. You absolutely have to have those. Okay? It's not an option here. So, average power delivered by an AC source is found by taking P average, which will then be equal to V RMS plus I RMS. Okay? Also, you can take I squared RMS times R. You know this equation. We're just using specific values. Or you can take V squared RMS over R. Or, okay, now these three are given to you. You could, average power would be the two maximums divided by 2. Okay? This one, not given to you at all. All right, so let's look at a quick example. So the first one, a voltage is supply stated as 6 volts AC. Calculate the peak output. This is always VRMS, okay? Unless they tell you otherwise. And they tell me they want peak. That means they want the maximum. So they've given us the VRMS. We want the maximum. We have our equation. So here we go. So 6 equals Vmax over square root 2, and Vmax is equal to 8,49 volts. Simple as that, okay? So this is fairly straightforward. Now they want, if the peak AC is 15, so in other words Vmax, calculate the RMS. So VRMS is maximum voltage divided by square root 2. So we're going to take 15 divided by square root 2, and we get 10,61. Nice and straightforward. Okay. A certain AC generator produces a peak current, maximum current, of 6,2 amps when connected to an electric heater. Calculate the RMS. So again, I RMS equals I max over square root 2 to give an equation. We dump in all the information we know, and we get 4,32. Okay. Nothing difficult about this. This is quite nice. So the only way they can make this difficult is like the next question. This is about as difficult as they can make this section. So they tell you you've got a diagram. I'm not worried about what's going on here, okay? In the given diagram, the AC source delivers a 15 VRMS to a speaker, and they say and assume that the only thing that influences how good the speaker is the resistance, okay? First thing they ask is for the peak voltage. Well, they've given you RMS, and that symbol, by the way, means alternating current. So we want peak voltage. We're okay. That was the easy part. Okay, nothing difficult. Straightforward into the equation, and off we go. Now, what we need to recognize about this particular circuit is that these are in series. In series. Now they want the RMS current. So when we look at this and we go, well, at the moment I don't even know peak. I don't know anything about the current, but I do know resistance. Whether you use VRMS over IRMS with resistance, or you use maximum and maximum, it doesn't matter. But you can't use an RMS value and a maximum value with resistance together. Okay, so either you use 2 RMS values or you use 2 maximum values. Now they want the RMS current. I know VRMS, we were given that. So I'm going to use R equals VRMS over IRMS. Gives me IRMS. Okay? Straightforward. Now they want the average power delivered to the speaker. Now you need to be careful, because you are going to be very tempted to use V, but you can't. There are 2 resistors in series. When they are in series, the potential difference splits. You know what the total is. You would then need to work out what the V is over the speaker specifically. And you're welcome to do that. But you don't need to, because you know the current through the speaker and you know the resistance of the speaker. So you can use the current and you can use the resistance as given. Please be careful with something like this. This question relies on your understanding of circuits, normal circuits, not anything with an RMS attached to it. Okay? All right. So just be careful. Then the last thing they ask you to do is to draw a graph of AC voltage versus time. Label the peak. when they ask you for a label, they want an actual value, and we got the value as plus 21,2, and then the bottom is minus 21,2. Please, they didn't tell you how many cycles to draw, so draw a couple so they can see exactly that you know what's going on. Okay, nice and simple. A good activity to do is activity 1 on page 321. 1, 2, 5, and 6, the ones I left out are quite silly questions, so you don't need to worry about those. The memos are on Teams for you. Okay?